All right, I do have your mini exams, the mini exam 4. So at the end of class, you can come grab these. I'll just put them up here, so just wait for now. The mini exam 4 grades were great because that test was very mechanical, tedious, but straightforward. There was no like trickiness to it. So the grades were real good. All right. We're starting chapter 12 today. Chapter 12 is called Multiple Integrals. Cal 3 is made up of 4 chapters. Chapter 10, which is where we talked about three-dimensional space, vectors, right? And then we moved into chapter 11, where we started talking about derivatives, partial derivatives, and we just finished up with max-min problems. And now we're moving into chapter 12, which is going to deal with integration in higher dimensional space. And then chapter 13 will take us into vector calculus, not vector functions. We'll be doing calculus with vector functions. So we are like at the halfway point in the as far as the 4 chapters are concerned, but chapter 13 is super dense, super dense. So this will be, I think, a little bit of a relief. Chapter 12 will be a little bit of kind of like, okay, this is all kind of stuff I've seen, just kind of thinking it from a different perspective. So, all right, chapter 12, section 1, double integrals. So we're going to start here by me reminding you how we came up with the actual fundamental theorem of calculus. And this is a very quick recap, okay? I'm not going into the precise details of Riemann sums and things like that. But in Cal 2, we should have walked away there understanding that if you take some function of x, right? Y is some function of x, and you restrict it onto some interval a, b, some closed interval, then we can start talking about the area, right? The area under that. And that's where the whole, antiderivative, the definite integral was used, right? But the foundation of that formula, right, that the area is the integral from a to b of f of x dx. That's our evaluation theorem from Cal 2. This is how you find that area, right? The whole idea behind this is that we imagined cutting this region that we're trying to find the area of into rectangles, and then taking n rectangles in this region, figuring out a formula for the area of all of those rectangles added together, and then we take a limit as we let the number of rectangles go to infinity, right? That's the basic idea. So if we look at one of these rectangles over here, if we want to find the area of just one of them, well, the height of the rectangle will be the value of the function at some point between the left and right endpoints of that rectangle. And it turns out in Cal 2 that it doesn't matter where you pick that point. It can be at the left or the right or the middle or any point in between. So I'm just going to call this some arbitrary point in here, x sub I. All right, so the height of this rectangle will be f of x sub I. The reason why it doesn't matter which point we pick is because when we take a limit and let n go to infinity, this thing is going to shrink down. So it doesn't matter if it's left endpoint, right endpoint, middle point. They all kind of converge together to one single point. So that's why it can be arbitrary between here and between the left and right. So that's the height of the rectangle. And then the width of the rectangle, we call that dx. Delta x, sorry. It's delta x before we take the limit. So this is delta x. And no matter which rectangle we're talking about, they all have that the same width of delta x. So we say, okay, well, then the area, right, the area should be approximately the sum of all of these areas. So it's like if we sum every height of every rectangle times every width. So the height of the rectangle times the width. Height times the width gives you that area. If we take the sum of each one of those and we let this go to infinity, right? The number of rectangles go to infinity, we get this, right? Does that all kind of ring a bell from Cal 2? Yes? So what I want you to see here is the similarity between this notation and this notation, right? You have this f of x is really like this, and the dx is really like the delta x. The reason why we use this notation is exactly because this represents the height and the width of the rectangles. And then the integral sign is basically us saying we're going to take the limit as we let the number of these go to infinity. Got it? Okay. Now, today, what we're going to do is this. We're going to say, what if we are interested in a surface? Okay, so let's imagine that we have a surface. Let me draw a surface up here for you. Okay, so there's some arbitrary surface up there. And what I want to do is restrict it to some domain. So on the ground, does everyone see on the ground? Let me take the surface out of there. On the ground, that's the x and the y axis. We look at it here from the top. Notice that my x's are trapped between two constants, and my y's are trapped between two constants. So this region, I'm going to call it capital R, okay? That region, the way we could write that is, it looks like the x's are between 0 and 2, and the y's are between 0 and 2. We write this, 0, 2, 0, 2. That is the notation that tells you that you're looking at a rectangle that is in two-dimensional space where your x values are between 0 and 2, and the y values are between 0 and 2. This is the way we write it. This is the notation for it, all right? So this is our restriction. So that back in Cal 2, this is like where we had a function and we started at A, ended at B. We had a restriction here between A and B. Here it's like a double restriction. We have a restriction on the x and a restriction on the y. Got it? Then a surface above it. And what we want to know is if you were to take just the points in this region, plug it into the function, right? You get, that's the image of that rectangle up on the surface. We want to know what you would get if you projected that image down to the xy plane. You'd get this solid object. So just like here, if we project this down, we get the area in here. Here we're going to talk about the volume of the solid below that surface and above the x-axis. So the volume of that. That's what we're interested in. Can we take an arbitrary surface, restrict it to some domain, drop that down and create a solid object, and then find its volume? So do you see there's a big connection here between these two? So how do we do it? Well, we do it just the way we did it before, all right? It's just going to look a little more complicated, and actually, I'll use this picture. It's a terrible picture. Must have been shaking when I was drawing it, but all right. So just like, I think I'll put the Cal 1 problem over here. Just like before when we had this, A and B, we took a rectangle in here. We picked some arbitrary point here, x sub I, right? And then we created this rectangle and we tried to find the area of that. Well, first thing we did was we took the interval, right, and we cut it into a bunch of pieces to create our rectangles. And then for each little piece, we just drew rectangle, 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 right, and found a formula. Here, we got to take our domain, which is the region that's on the ground, right? So in that picture that I just drew where it was 2 by 2, right, imagine that that's what this is. So our x's are restricted between two constants, A and B. Our x values, our y values are restricted between C and D. So we take that and we cut that region up into a bunch of little rectangles, or a bunch of little squares. And each square within that region will have a delta x and a delta y. So a little change in x and a little change in y. And so what we do then is we take one arbitrary point in that little rectangle and we plug that into the surface which is this point somewhere in here, gets plugged into the surface, and up here on the surface, the surface is up here somewhere, that will give us the height of that parallel piped box, right? And so we want to know what is the volume of this box. And then if we can find the volume of it, we'll add them all up with an integral by letting a limit go to infinity, right? So the volume of that single box would be the height of it, which is this, times this width, which is delta x, delta y, right? So this little formula would give you an approximation of the volume of one of those boxes. Yeah? Now, we just need to add them all up, right? We just need to add them all up. Add up all the boxes, yes?
Does the domain have to be rectangular?
Today, well, first part of today, yes. Next part of today, no. So right now we start on rectangles and then we go to different types of regions on the ground. So we need to find a way to sum, okay? We need to find a way to add these things up, right? So one thing we could do is imagine first taking all the rectangles in this x direction. We could add up all of those, right? Add up all the x direction rectangles. And then after we do that, kind of move up and then add across again, then add across again, add across again. So it's you sum across the x's and then move up on the y and sum across the x, move up on the y, sum across the x, and just add all those up. So it's going to require a double summation, a sum of two different things. My notes, this is all my notes. It's written much clearer than this because I have it typed up here in a second. But this is me just again showing. In order to find the volume, the total volume over that rectangle R, we're going to require a double summation of those volumes of those boxes. And so if we take the limit, what we should expect then is to get a double integral, two integrals. The first integral to take care of the first summation, and the second integral to take care of the second summation. That make sense? Which is the idea of this section, double integral, right? Okay. Let's get to a formula. That was all just so that you can be convinced that the idea of a double integral comes from the idea of a double summation, which is required to add up all the volumes of the boxes. Yes?
So it's just like a distance summation where you have to do one before the other, like the inner then the outer?
Yeah, you don't have to start on the inner and then go to the outer. Exactly. So you sum through the first one, and then after you're done, you sum through the second. Yeah.
So it matters what variable.
We'll see. We'll see. In some cases it matters, some cases it doesn't. We're going to see. All right, so right here, this is just notation. I'll make it a little bigger for us. All right, the volume, okay? The volume between a surface f of xy and the xy plane, which is the ground. So if you want to find the volume between the surface and the ground over some rectangle R that is defined to be the closed interval AB, so this is our restriction on x. I don't know how you want to say that. You can say crossed if you want, but don't think about cross product, okay? AB cross CD, right? That is given by this notation. Pay attention to this one first. We write double integral over R. This R is telling us the region. This is going to become extremely important in chapter 13 because we're going to be doing integrals over all sorts of different things. Sometimes this is a vector field. We have to understand what this R is. In this case, R is a rectangular region on the ground in two-dimensional space. So we're doing a double integral over that. What are we adding up? Well, this f of xy was that height of that box, right? This box here, right? This height was f of xy. Now, it's really x sub 1, y sub 1, or x sub 1, y sub, sorry, let me say it again. X sub I, y sub j, because you're doing a double summation. You're summing over one, then summing over the other. But when you take the limit, everything becomes just x and y in our formula. So that's the height, and then the width is now dx, and this is dy instead of delta. So that's this, right? Do you all see that? That's this. Is your height, dx dy. Now notice here it says dA. Capital A here represents the area of that little box. So I want to point that out again, because later on that's going to be like, this might be a vector field, so we need to know what the A is. The dA, that is that little box on the ground. Okay, that's the box on the ground where this side is dx, this side is dy. So we're talking about this piece right here. That right there. We call that d capital A, all right? So you're doing a double integral over the rectangle R of the scalar function. That's a scalar function because it takes in numbers and spits out a number, right? Scalar function times dA, which is the dx times dy. And then you convert that to this notation where now you actually put limits of integration, right? Limits of integration. Notice here that on the first integral I have a to b, right? Second one c to d. Remember that the a to b is a restriction on x. So if you look at this, there's almost like a hidden parentheses right here. It's like you have an inner integral and an outer integral. On the inner integral, you're doing everything with respect to y, and then after you've done that, you're going to do everything with respect to x. I'm going to show you the next note says that explicitly. This can be written this way, or this also means, these are the exact same things, you could do it the other way. You could do the y's on the outside and the x on the inside. Next note, which is very similar to the note I just put on the board. Iterated integrals. So this is just exactly what I said. This notation really means this. Okay, it's like you have an inner integral and an outer one. When we look at this inner integral, when we look at that, since it says dy, we will treat y like our variable, and we'll treat x like a constant. Then when we get to the outer integral, x will be our variable, and y will be treated as a constant. Or we could switch the order, and we could do the x part first, treating x like the variable, y like the constant, and then once we do that, we will do the opposite, treat y like the variable, x like the constant. I think the best thing to do is do an example, right? We can sit here and look at formulas all day. Can you stop, please? It's distracting. Thank you. All right, so find the volume under this. I give you a surface, right? Do we know what that looks like? Maybe we go back to our, it's like a paraboloid looking thing. Like if it were just this, I think most of you would say that's a parabola that opens down, right? If I get rid of that, you'd still say it's a parabola that opens down. So both of them together should look like this paraboloid thing, right? Which is in fact what it looks like. Oops, I gave it away already. There we go. There's our surface. So there's our surface, and we are restricting it to 0, 2, 0, 2, right? So we're trying to find that volume. That's the picture I started with a minute ago, all right? All right, so let's just do the work, all right? I'm going to choose, I get to choose, I'm going to do the integral with respect to y and then the outer integral with respect to x. So first I'm going to start this out. I'm doing the double integral over r of this function f of x, y, with respect to the area. Hear me say that? With respect to the area. I'm going to go integral from 0 to 2, integral from 0 to 2. Now the function 16 minus x squared minus y squared. 2, oh, thank you. 2y squared. I didn't even realize that was 2y squared. 2y squared. And then, well, they're both 0 to 2, right? So it doesn't really matter which one I do first. But I said I was going to do the y first, and then I'll do x. And I'm sure you're sitting there and go, it doesn't matter, right? Can I do it the other way? Will you get the same answer? So spoiler alert, yes, you can do it each way. You can do it either way, your choice, as long as this is a rectangle. Okay, that's coming in a later note. All right, so let's focus our attention right now on this inner integral. Now, some professors, what they do is they go to the side right now, and they do that integral over here. And then whatever they get as an answer, they come and they bring it back here. And then other professors, what they do is they work with it like, you know, this equals the next line equals the next line. They never get rid of the outer integral. That's the way I do it. I keep all my notation together. So my next line is going to be this. Equals, okay, the outer integral. Give myself plenty of room, just so you can kind of see what I'm doing here. I'm doing the outer integral. All right, so that's still the same. I haven't touched that. But on the inside, what I'm going to do is take the antiderivative of each of these, treating y like a variable and treating x like a constant. So the antiderivative of 16 should be 16y, right? So 16y. Then minus, now x is a constant, right? So x squared is a constant. So the antiderivative of a constant should be that constant times the variable y. So I should get minus x squared y. We're doing antiderivatives, right? Not derivatives. And then the antiderivative of negative 2y to the second. Y is my variable, so I'm just going to do the power rule for this, which means I have to add 1 to that and then divide through by that. So should get negative 2/3 y to the third power, right? Now, I do not put plus c because this is a definite integral. I have limits of integration. So now this is a good place to put the, I don't know what your previous professors call this, evaluation bar. The evaluation bar. So this is the place where you can put your two limits of integration. So I want us to get into a habit that we maybe didn't do in Cal 2. And that is when you put, in Cal 2 we just put the numbers here, right? It was just 0 and 2. But because we now have more than one variable here, I want us to be very explicit about what it is that is 0 and what it is that is 2 here. So what variable are we dealing with right now? Y, right? So I'm going to put y equals 0 to y equals 2. Do you see that's usually a little different for students that they didn't, in the past have to actually put that there. But we're going to have x's, y's, z's, we're going to have r's and thetas later, and we're going to have to be keeping track of what's our variable. So we want to make sure that we know exactly what we're going to be plugging in, right? I'm going to be plugging in 2 for y, right? And 0 for y, not for x. All right, let's do it. We're going to plug in now, all right? So my next line, going to go above this. Integral 0 to 2. Still haven't done that yet. Plenty of room here. Dx. Okay, when I do the evaluation, what I like to do is do 2 sets of parentheses. This is us using the evaluation theorem, the fundamental theorem of calculus. We're going to plug in 2, put it here. We're going to plug in 0, put it here, and then of course you subtract. That's the formula, right? So plug in 2 for y. Let's see, we get 32. And then minus, we're plugging in 2 for y, so minus 2x squared. And then 2 for y, here we get 8. And then times 2, 16 divided by 3, so 16/3. Okay, that's plugging in 2 for y. And then when we plug in 0 for y, kills everything off and we're happy. Next line. Equals integral 0 to 2. Okay, these are both constants, right? So I could put those together as long as I have a common denominator. So 3, 36, what is that? 20? What is it? Sorry. I'm doing 96, 80? My brain, whenever I do this arithmetic, my brain just stops. Like I just don't even want to do it. My brain, so we're just multiplying. 80? 80, right? Okay, 80 over 3. 80 over 3. Minus 2x squared. Dx, right? We're back in Cal 2 now, right? Right? Aren't we back in Cal 2? Yeah. So now we just find the antiderivative of this and we're in business. So antiderivative there would be 80 over 3x minus 2/3 x cubed. And then the evaluation bar, x equals 0, x equals 2. I really don't need x equals 0, x equals 2, because there's only one variable here, right? But I'm going to start to be consistent with this. Any questions? Just plug in now. I already know this one's 0, right? The second one's 0? Okay, so that's good, nice. The other one I plug into, I get 160 over 3 minus, and then there I have to cube it, so 816 again over 3. And then that's 144. 144 over 3.
Should reduce 48.
48? 48. That's the volume of the solid underneath that surface between 0, 2, 0, 2. It turned out to be a nice number, okay? I mean, it's just happened to work out that way. What's more important here is the actual mechanical process of this, right? Does this seem pretty okay to everyone? A little bit.
It's like partial derivatives, but backwards.
Kind of, yes. I mean, what we're doing is holding one variable constant, right? And then integrating the other one. So it is. But there's another thing we're going to do later that's actually called partial integration that is a little bit different, so I don't want to use that terminology. All right, let's see where we're going next. Find the volume under y sine xy on x between 1 and 2 and y between 0 and pi. So notice that my x and y restrictions here are not the same numbers this time, right? It's not 0, 2, 0, 2. It's 1, 2, 0, pi. So I need to just be careful when I write things down. I'm going to do this exactly the same way as I did the previous one. I'm going to say first, I'm doing the double integral over r, and here r is this, right? That region of the function f of xy with respect to the area. This will be equal to, now I actually put my limits of integration. I'm going to do the x on the outer one, so 1 to 2, and then 0 to pi, right? And then the function itself, y sine xy. This is still a box. Well, what do you think? Is it? Yeah, your x's are between two constants, right? Your y's are between two constants. So yes. dy dx, right? Now I don't have a choice. I cannot just arbitrarily flip these. The y is on the I can't say that today. The y is on the inner integral, and the inner integral has the limits 0 and pi, which are my limits on y. So I need to make sure I get that in the right order. Now this is equal to the integral from 1 to 2. Okay, this is my outer integral. Let me just put this here. I may not need this much room, but I'm just going to do it just in case. All right, I've got to find the antiderivative of this, right? That's my next task, is to find the antiderivative of y sine of xy, treating y like the variable and x like a constant. So how am I going to do that? How am I going to do that? So wait a minute, let's time it. I'm going to go do some scratch work, okay? So I'm going to erase this so I can do some scratch work. I'll come back to that step in a moment. I need to figure out what is the, just forget there's even any limits of integration. What is the antiderivative of y sine of xy right, dy, and I'm treating the x like it's a constant, right? So just to help myself understand what I need to do here, I'm just going to throw an arbitrary constant there to help my brain like comprehend what's going on. Basically, I'm trying to do a problem like this, right? And the x is just some constant. So I look at it and I realize that's going to require integration by parts. That's going to require integration by parts, right? So I've got to do integration by parts. Now, there's a million ways that people are taught integration by parts. So my expectation is that you can do it. I'm just going to do it my way over here. And if you're looking at my way going, I don't know what he's doing, just do it your way then, all right? We should get to the same answer. So I teach my Cal students to use this little like grid, and then basically they have to come up with what U and dV is. This is that whole ultraviolet minus voodoo thing. So you choose which of these is going to be your U and which is going to be your dV. In this case, I would choose my Y to be my U, and I'd choose my sine of 4y dy to be my dV. And then I'm going to differentiate this and integrate that, and then I'm going to use the formula. So if I differentiate this, du becomes dy, and then v here becomes the antiderivative of this, which would be, careful, 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 negative. It's negative, I agree. 1/4 cosine 4y. The antiderivative of sine of 4y is negative 1/4 cosine 4y. Because you have to scale out, right, to kill off that 4 that comes out with chain rule. You have to kill it off. So you have to put a 1/4 out here, and it has to be negative because the derivative cosine is negative sine. And okay, so get all that Cal 2 juice stirred up and get it back up to the top here. All right, now that's just setting up, and now I need to do the formula, which is ultraviolet minus voodoo. So it's this times this, right? Yes? What for? I'm making it up. It should be an x, right? It should be an x. Yeah, it should be an x, but just to help our brains process what we're doing so that the x doesn't confuse us, I put a 4 in there. I'm about to replace it with x. Okay, yeah, all right. If you don't need to put the x. This is the first example, so I just, I put a 4 there. So what is our ultraviolet? These two multiplied, so I'm going to put negative 1/4 y cosine of 4y, and then minus, I like to leave space in the front in case I need to pull a constant out. Now it's these two multiplied together. So I actually do have a constant I can pull out, right? Negative 1/4 can come out of this in front here and become plus 1/4. And then cosine of 4y dy. And then I'll have to take antiderivative of that, which should be okay for me, right? So still continuing over here, I've got that equals negative 1/4 y cosine of 4y, and then plus 1/4. But then when I take the antiderivative of that, I'm going to have another 1/4, but now sine of 4y.